Springs and elastic potential energy are going to be the topic of this lesson in my brand new general physics playlist, which will cover a full year of university algebra-based physics. Now, in the last lesson, we learned about the conservation of mechanical energy, which is the sum total of both potential and kinetic energy, but we only learned about gravitational potential energy. In this lesson, we'll incorporate elastic potential energy stored in a spring. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, if you're new to the channel, we've got comprehensive playlists for general chemistry, organic chemistry, general physics, and high school chemistry. And on chadsprep.com, you'll find premium master courses for the same that include study guides and a ton of practice. You'll also find comprehensive prep courses for the DAT, the MCAT, and the OAT. So let's talk a little more about that restoring force of a spring. And it turns out it's governed by what we call Hooke's law, which is F equals negative kx, where F is the force, x is the displacement from what we call the equilibrium position. So there's a natural position for a spring where it would be just naturally if no forces were acting on it. So we call that the equilibrium position. And if you stretch it from there or compress it from there, then there will be a restoring force. But at that natural equilibrium position, there's no force. And so at the equilibrium position, x equals 0, and so the force equals 0 as well. All right, so it turns out, though, you can see that from Hooke's law, the force is proportional to that displacement away from the equilibrium position. Whether it's stretched or compressed, it doesn't matter. So if you double the displacement, you'll double the force. If you triple the displacement, you'll triple the force. So it turns out that the restoring force here is also proportional to that k, and that k is a proportionality constant here that we call the spring constant. And so typically stiffer springs we associate as having a larger spring constant and therefore require more force to either stretch or compress. Looser springs have a smaller spring constant and will take less force generally to stretch or compress. So that's kind of where that comes into play. But also notice this negative sign here. So the restoring force is always in the opposite direction to the displacement. If you are stretching a spring, the restoring force is working to compress it. If you're compressing a spring, the restoring force is working to stretch it back out the opposite direction. So that's what the negative sign is there for. So, and one source of confusion here is a lot of students think, well, okay, so we're talking about F equals negative kx, the force it required to pull the spring back. Well, that's not technically what Hooke's law has given us here. So that would be an applied force. So again, as we stretch the spring, that applied force, Hooke's law shows us the force that's opposing it. Now, it turns out if you want to stretch it at constant velocity here, well, the exact force you'll need to apply would be the force according to Hooke's law, at least in magnitude. It would just be in the opposite direction. And so if you're talking about the actual applied force to stretch it or compress it, well, that force is going to be in the same direction as the displacement, and we could just use F equals kx for that. But Hooke's law properly is giving us that restoring force, that conservative force that makes potential energy possible. And if we take a look at that potential energy, new type, it's called elastic potential energy. It turns out it's equal to 1/2 kx squared. Now, it turns out if we want to actually find where this comes from, we'd need a little bit of calculus, which we don't need in this class. So, but it turns out that, we'll see this in a little bit later lesson, that the true definition of work is the integral of f dx. Well, if f is constant, that would pull out in front of the integral, and that's all we've dealt with so far is just constant forces. And that's where our definition of work equals f delta x would come from, taking a very simple integral of dx. But what if your force itself is dependent upon the displacement? Then it's not constant and you can't pull it out. So, and you'd have to, substitute in here negative kx. And well, it turns out that's where this idea of elastic potential energy would come from, is taking that integral. And again, you don't have to solve that integral for this class. If you're in a calc-based class, sorry, we're not doing that integral. But that's ultimately the integral you'd be solving for. But once you do, you will find out that the opposite sign of that work is the elastic potential energy you're giving that object, and it comes out to 1/2 kx squared. And so we can see here that in the same way we saw with Hooke's law, so now this potential energy is going to be proportional not to the displacement, but to the displacement squared. So if you double the displacement away from the equilibrium position, it's not going to double the potential energy, it's going to quadruple it, doubled squared, if you will. But that potential energy is indeed proportional to the spring constant. Double that spring constant, it doubles that elastic potential energy as well. And that makes sense. A stiffer spring, so for a given displacement, should store more energy than a looser spring for that same given displacement. Okay, So these are the couple new equations we're dealing with in this section. So Hooke's law with the restoring force and then the corresponding elastic potential energy. Now we're going to cover springs in a little bit greater detail in a few chapters in a slightly different context. We'll incorporate this, but we'll add some more stuff as well. So if you're looking for some more details, that's coming down the road in a little while. All right, so we got to take a look at our definition we were using for conservation of mechanical energy and alter it just a little bit. So we said that conservation of kinetic energy, so the initial kinetic and potential total is going to equal the initial kinetic and potential final. That is still true. Now what you're going to find though is that now instead of dealing with gravitational potential energy, you're going to have problems dealing with elastic potential energy in this section. So instead of mgy, we'd now have 1/2 kx initial squared, 1/2 kx final squared. Now the truth is we're making an assumption here that gravity is not playing a role in some certain problem. Well, the truth is this though, we now have the possibility of having more than one type of potential energy. And it doesn't specify which type, it just says potential energy total. And so if you had a problem that involved both gravitational potential energy and elastic potential energy, you'd have to have both those terms in this equation. We'd really have 1/2 mv initial squared plus 1/2 kx initial squared plus mgy initial equals all three of those terms corresponding final. And again, later on in this course, we're going to find out that there's also rotational kinetic energy, and we can add that term in. Now here's the deal. Most of the problems you're going to deal with though aren't going to be quite that crazy. And so most of the time you're really going to have one type of kinetic, one type of potential in most problems. And that's why the setup's going to say fairly simplistic. However, we now understand that, well, all you have to do if you have more than one type of potential or more than one type of kinetic is just add another term to both sides of this equation. Just keep that in mind. All right, now I think we're ready to work some problems. Nope, not yet. We got one more thing to look at. So the context we're going to study this in a little bit, in a few chapters, what we call simple harmonic motion. So if it turns out if you take a spring, and it turns out this slinky is not a true spring, it's more of a coil. And the reason being is that if you extend it, it will snap back, but you can't compress it to any significant amount from its original position. So it's not a true spring. But I'm still using it because one, it was cheap, it was less than $4. But two, it makes a great visual demo in a way that I'd have a tough time locating an adequate spring to do so. But if we do elongate this, it will snap back. Now in simple harmonic motion, what happens is that if you let it snap back, the spring's just going to oscillate back and forth, and it's going to go from points of being maximally displaced to the other side of being maximally compressed, and then passing through the equilibrium position in between as well. So let's take a look at what this means in the context of our problems here. So again, there's some natural equilibrium position at which it's not stretched or compressed at all. And again, the slinky is not a great demo for that particular point because this thing likes to stay in its equilibrium position fully compressed. That's not great. Again, not a true spring. But for a true spring, its equilibrium position, again, would be when the displacement equals 0. All right, you compress it from that point or stretch it from that point, and all of a sudden now you're going to have a restoring force according to Hooke's law. But at that point, at that equilibrium position, if x is 0, then your restoring force is 0 as well. There's no restoring force there whatsoever. All right, so let's see how this kind of works. So in this kind of simple harmonic motion as it's oscillating, and again, the simple harmonic motion, the bigger the initial stretching force that once you release it, the greater it's going to be its oscillations. But for any given set of oscillations, you're going to have a point of maximum displacement. On the one side, maximum compression, and on the other side, maximum extension. And it doesn't mean it's the maximum for that spring, it's the maximum for that given set of simple harmonic motion. Again, you could stretch it initially even further, and then those maximums would change, and they would go up as well. But for a given set of simple harmonic motion circumstances, it's the maximum in that context. All right, so if here you're at a maximum displacement, and same thing over here, well, that's going to tell us some things from our equations. Let's take a look. So if you're at a maximum displacement, that means you're going to have the maximum restoring force applied as well. So we get a maximum restoring force there, maximum restoring force there, and here that restoring force is going to be 0 at the equilibrium position. Well, according to Newton's second law, force equals mass times acceleration. And so if the force is at a maximum here, well then so is the acceleration going to be at a maximum here. But again here, if the force is 0, well then the acceleration is going to be 0 as well. Okay, one more thing to talk about in this regard. So in this case, we got this combination, this oscillation of potential and kinetic energy everywhere along this motion. So mechanical energy is going to be conserved. It's going to have the same total. But what we can find out here is that, like at this point right here, x equals 0. And if x equals 0, well then the potential energy is going to equal 0 as well. So if the potential energy is 0, and again, the total mechanical is the same all the time, well, if the potential is 0, well then it must be all kinetic. And so the kinetic energy is going to be at a maximum. And don't forget that kinetic energy, 1/2 mv squared, means that your velocity must be at a maximum as well, in that case as well. So if we look at the other direction though, so when this thing gets fully compressed, this spring, or fully extended, that's when it is going out one direction and then changes direction to snap back. And that should sound a little bit familiar. Again, if we look back at projectile motion, when you threw an object up in the air, it slows down, slows down, slows down, and for a split instant, it stops, it has a velocity of 0 before heading back down. So again, whenever something changes direction, for a split instant, it has a velocity of 0. So when it changes direction completely anyways in the opposite direction. So, and that's true here on the springs as well. At the point of max compression and max extension, for a split instant, the velocity is 0, which means it has no kinetic energy, all potential energy. And so in addition to saying that we got maximum kinetic energy at the middle and no potential, at the extremes, the point of maximum displacements, we have all potential energy and no kinetic energy, with the velocity being 0. So, and these are just some things to keep in mind. So, and again, anywhere in this motion, you could be somewhere in between max compression and the equilibrium position, and the total kinetic and potential total would still add up to the same total at any other point. So, but just like we saw with gravity, it was convenient. If we were dropping something, well, at the top, when we drop it from rest, it has no kinetic and all potential. And right before it hits the ground, it has all kinetic and no potential. And we look at the extremes. Now, it turns out, again, anywhere in its motion, though, the total of kinetic and potential would add up to the same thing. But in the middle of its motion, it would have both kinetic and potential. Same thing's true of the spring. If you're somewhere in between max compression and equilibrium, or max extension and equilibrium, you're going to have both kinetic and potential. Well, what you find is that we often deal with the extremes because that's where we can solve problems, because one of those terms is going to go away, being 0. And again, at the equilibrium position, all kinetic energy, velocity at max, no potential energy. At the extremes, all potential energy, no kinetic energy, velocity is 0. All right, let's work some problems. All right, so first question here says a 50.0 Newton force displaces a spring 10.0 centimeters from its equilibrium position. What is the spring constant? And what would be the displacement resulting from a 250.0 Newton force? So two questions here. We want the spring constant being given the force and the displacement. So, and we should realize force, displacement, solve for spring constant. That's Hooke's law. Sort of anyway. So Hooke's law says F equals negative kx. And what we got to realize again is that for Hooke's law, the force that's given is the restoring force. So to go along with that displacement right there. And again, the negative sign shows they're in opposite directions. Well, in this case, we're not actually told the restoring force. We're told the applied force that's working against the restoring force. So again, a 50 Newton force displaces a spring. It's what's working against that restoring force. And so for the applied force working against it, it's actually just F equals positive kx. So the force and the displacement are in the same direction for the applied force that's stretching or compressing the spring. So that's why you might wonder sometimes, where did the negative sign go? Well, were you talking about the restoring force, or were you talking about the applied force working against the restoring force? All right, so in this case, we want to solve for that spring constant. Rearrange this. We can see the spring constant is equal to F over x. So force is newtons, x in SI units, displacement would be in meters, and the SI unit for a spring constant is newtons per meter, which is the way this should work out. So again, that's 50.0 newtons over 10 centimeters would be 0.1 meters. We can see this is going to come out to 500 newtons per meter, but if we want the proper number of sig figs, and it looks like we're going to need 3. I hate putting lines over 0, so it's going to be easiest to do this in scientific notation to get 3 sig figs. So 5.00 times 10 to the, let's see if we can write 10 correctly, 10 to the second newtons per meter. That is our spring constant. Okay, so second half of the question here So what would be the displacement resulting from a 250 Newton force? Now we're set up to actually use this equation one more time here, because now we're given a new force of 250 newtons. We now have the spring constant for this spring. That doesn't change. So we could plug in right there and then figure out the new displacement. Or we could take what we remember about Hooke's law, is that the force is proportional to the displacement. You double one, you double the other. Well, in going from a 50 Newton force to a 250 Newton force, that's 5 times more force. It should result in 5 times greater displacement then. And so going from 10 centimeters, that means we're going to go up to 50 centimeters or 0.5 meters. Now, if you could reason that out and see that proportionality, great, it's going to save you a lot of time. So if you can't, you can still get it with the calculation. It just would have been a little more work. So in this case, then, we could say again that the 250 Newton force equals our 500 Newton per meter spring constant times x. And solving for x here, we're going to get 250 over 500, which is a half, or 0.5. And that's going to be in units of meters. You can see the newtons parts are going to cancel out. So, and again, 0.5 meters is the same as 50 centimeters. If this were multiple choice, either one of those I could envision being an answer choice on a multiple choice question. Oh, and we should have done one thing, right? This was supposed to have 3 sig figs. So how about 0.500 meters to make that a little bit better? Next question says a spring with a spring constant of 800 newtons per meter and a 0.5 kilogram mass on the end is stretched horizontally 10 centimeters from its equilibrium position on a frictionless surface, and released. What is the velocity of the mass on the end of the spring as it passes through the equilibrium position? Okay, so we're going to stretch this spring to a point where it's the maximum extension, if you will, for this given situation. We're governing it, however far we stretch it, that is the point of max extension, because when we release it, it'll never go back out any further than that. It'll go back out to that exact displacement every time it oscillates, but never further. All right, so we're starting with that point, the point of max extension, but then we want to know what is the velocity of the mass on the spring when it passes through the equilibrium position. And again, we're going to take into account conservation of mechanical energy here, where we can say that the kinetic energy initial plus potential energy initial equals the kinetic energy final plus potential energy final. And one thing to note with this kind of oscillatory motion, stuff like that, defining things as initial and final is a little strange because there's no initial final. This thing is just going to oscillate forever if no other forces act on it and stuff like that. So sometimes you'll see this written instead of initial and final, you'll see people just use at position 1 and position 2 during the motion. Well, that's great too. It doesn't have to actually be initial and final. It could be any 2 positions in the motion. And so the positions we're going to use here are going to be the equilibrium position here, and then here the point of max extension right here. So because we know some things about these 2 points on the extreme. So one, we know that at the point of max extension, there's no kinetic energy. The velocity is 0. That term's going to go away. And at the point of the equilibrium position, which is, again, we want the velocity at the equilibrium position, so being part of that kinetic energy term, we know that there's no potential energy because there's no displacement. And again, if the displacement is 0, then the restoring force is 0, and there's no elastic potential energy as well. All right, so this should look somewhat familiar to some of the stuff we did with gravitational potential energy here, where some of those terms go away at the extremes. And so we're going to have 1/2 mv1 squared equals 1/2 kx2 squared. And from here, it's going to be a little bit of plugging and chugging. So we want to again solve for that velocity right there. So notice the 1/2 will cancel. We'll just get rid of those. We get v1 squared is going to equal k over m times x2 squared. And now we can start plugging some numbers in. So spring constant was given as 800 newtons per meter, 800.0 technically. Mass was given as 0.5 kilograms. So, and then the position of max extension, we stretched it maximally 10 centimeters, which is 0.1 meters. Don't forget to square it, most common mistake students make. And now we can solve for that velocity through the equilibrium position. All right. Is there any chance we want to do this in our heads? Oh, sure, why not? If you look at this, 800 divided by a half. Dividing by half, same thing as multiplying by 2, so 800 goes to 1600 in such cases. And then if you multiply by 0.1, we're going to do it squared, I realize, but multiplying by 0.1, 1/10, just move the decimal back one place. So we had 800 over 0.5 is 1600. Multiplying by 0.1 takes us back to 160. Multiplying by 0.1 again, because it's squared, takes us back to 16. So we can actually do this in our heads and get 16 meters per second. If we look back at the problem, it says, looks like we're gonna be limited by the 0.50 kilograms to get 2 sig figs. And that's 2 sig figs. There should be our answer. So on something like this though, I highly recommend you let your calculator confirm this for you. So 800 divided by 0.5 times 0.1 squared, and it is indeed 16 meters per second. Okay, so the last problem here says, a 50.0 gram ball is fired straight up into the air by a spring constant's given as 800 newtons per meter, that is compressed 0.1 meters below its equilibrium position before being released. What is the max height reached by the ball? So we got a compressed spring here, it's going to be released, and it's going to fire this 50 gram ball up into the air. In fact, let's get that on there, 50 grams. So, and we want to know what is the max height actually achieved by that ball. That's the question. Okay, so a little bit different problem here, but we can look at this and talk about conservation of mechanical energy again. As long as there's no air resistance or friction, we can totally know that it's only conservative forces acting on there and the conservation of mechanical energy is going to apply. What's different about this problem, though, is that there's more than one type of potential energy, and we alluded to such a situation at the beginning where you might have multiple potential energy terms on both sides of this equation in some cases. And that's going to be the case here. And so if we try to write out the conservation of mechanical energy, we're going to have kinetic energy plus potential energy, and we got to do multiple terms here. So we're going to have potential energy of gravity plus potential energy elastic. So, and these are initial, and then kinetic energy final plus potential energy gravitational final plus potential energy elastic final. So and all of a sudden we start having multiple terms. Now, if we look, this is not really as bad as it initially looks here because we can take some things into account. So initially when that spring is compressed 0.1 meters, that's the maximum compression we're ever going to witness in this problem, right? It's not going to get compressed further. It's going to be released at this point and fire upwards. And so initially, it's got the maximum amount of of elastic potential energy. So, but this is also the lowest point on the entire trajectory. It's never going to get lower than this. It's customary, where there's problems with gravitational potential energy and gravity in general, to define the lowest point as kind of the 0 point. And if we do, well, then this gravitational potential energy is going to be 0 initially. We can get rid of that one. We're also starting from rest. Before it's fired, this thing is not moving, it's not in motion. So with 0 velocity, it's going to have 0 kinetic energy as well. And this problem's starting to look a little bit better. Some of these terms are going away. So we also know that in projectile motion, when something reaches its maximum height, like it is right here, that's when its velocity reaches 0. Great, because if its velocity is reaching 0 at that point, well then it's not going to have any kinetic energy at that point. So, and also this thing's not even in contact with a compressed or a spring at all, whether it be compressed or elongated or anything. And so there's definitely no elastic potential energy associated with the ball up here in its motion either. So the only thing we have is gravitational potential energy. And so our conservation of mechanical energy is really simplified here. So if we write some terms in then, our elastic potential energy is 1/2 kx squared, we'll take an x initial squared, and that's going to equal our final gravitational potential energy of mg y final. Cool, and that's that y final we want to solve for, and it's just simple plug and chug in this case. Now, notice anywhere along its motion, the total kinetic and potentials is the same everywhere with no non-conservative forces acting on it. But again, picking the extremes is often what we do, and in this case, because we wanted the max height, we had to pick that as one of the points. Well, the only other point we actually know something about is that initial point. It's the only real points we could have chosen. But if we want to know what's the total mechanical energy at any point along here, it's going to equal this, or it's going to equal this. It equals the same total at any point, including the initial point or the final point. So just keep that in mind. All right, so if we take a look at that final height, it's going to equal 1/2 kx initial squared over mg, and we can start plugging some numbers in here. So spring constant was given as 800.0 newtons per meter. So 0.10 meters squared for the displacement initially. Mass of the ball is 50 grams. That's 0.05 kilograms. Make sure it still has 3 sig figs. And then gravity is 9.8. And now we got some serious plugging and chugging to do. Now, if you wanted to ballpark this in your head, you probably could. 800 times 0.1 is 80 times another 0.1, since it's squared, gets you down to 8. 1/2 of 8 is 4. So 4 divided by 0.5 would be the same thing as multiplying by 2. Dividing by 0.05 is the same thing as multiplying by 20. And so in this case, 4, so over 0.05, or 4 times 20 is 80, and divided by another 10 would be roughly 8. So we're expecting this to be about 8 meters. So if you want to ballpark it in your head, but let's definitely let our calculator do some work for us. So 0.5 times 800 times 0.1 squared divided by parentheses 0.05 times 9.8 and my parentheses, and we're going to get 8.16 meters. If we look at all our numbers, we really need 2 sig figs there. And so we're going to round that to 8.2 meters. And indeed, we said it should be right around 8 meters. We realized instead of using 10 for gravity, so we're dividing by the true value, which is a little bit lower, we should end up with something just a little bit higher than 8 meters. If you found this lesson helpful, consider giving it a like. Happy studying.